This is my brand new custom-built satellite called SatGus, and in about a month, she'll be zooming by way up in space at 5 miles per second. But what makes SatGus so special is that she's got a phone right here and a camera right here, and her sole purpose is to take your selfie in space with the Earth photobombing you. And it gets even cooler, because if you tell me the city you live in when you upload your picture to the satellite, we'll not only take the selfie over your city, but we'll tell you precisely when that will happen. So if you go out to your yard and wave, you'll technically be in the photo twice. It's incredible we live in a day and age where just an everyday civilian like you and me can just decide to build something and then send it to space. So today I'm gonna give you a 6-step crash course that will tell you all you need to know to build and launch your own creation to space one day. And these 6 steps are very near and dear to my heart, because these are the exact same 6 steps I first learned when I was a young engineer at NASA working on the Mars rover. So for step 1, right out of the gate, you gotta first design your creation digitally in CAD. And that stands for computer-aided design, and it's really the first step for anything that gets made and manufactured these days. From a Mars rover, to a phone, to a hammer, to a shampoo bottle. CAD is critical for visualizing what it will look like and helping make design decisions about what should go where. In our case, after a few months of the design phase, we landed on something that looked like this. And it might look really impressive, and in many ways it is, but we sort of cheated and saved ourselves a lot of time and money because this is something called a CubeSat. About 25 years ago, a couple Stanford professors realized every satellite that goes to space needs all the same basic elements like solar panels, radios, and computers. So instead of everyone having to start from scratch and reinvent the wheel every time, they standardized the basic necessary hardware and sizes. Of the most common sizes used, the smallest is a 1U satellite, which is just a little bit bigger than a Rubik's Cube. And then there's the 2U, which is just 2 Rubik's Cubes, so double that. Then the 3U, the 6U, and the 12U. And this is the size we're using for SatGus. The way it works then is all the hardware necessary for the basic functionality of the satellite, like the flight computer, takes up this space. But then that leaves all this extra room for the payload. In other words, the purpose of your satellite. Like, what do you want it to do? In our case, that would be a camera and a screen for taking the pictures. So for your first creation you'll be sending to space, I highly recommend you make it a CubeSat, because that will reduce your development costs 100 times, from tens of millions of dollars to hundreds of thousands of dollars. So I want to talk about what's actually on SatGus, because you'll need a lot of the same hardware yourself. But first, let's talk about what makes it unique, which is our payload, or how we're going to take the pictures. Once we get to space and everything's looking good, these 2 spring-loaded panels rotate open. On one, we've got a Google Pixel phone in a radiation-resistant case, and then on the other, we've got a camera that's specifically been designed to withstand the harsh space environment. So once we beam your picture up to the satellite, we'll display it on the phone screen, and then the camera will take an HDR picture and then beam the image back to Earth. And you'll notice there's actually an identical setup of a phone and camera on the other side of SatGus as well. That's basically a full backup system, since we can't go to space and fix things if there's a problem with the primary camera. For power, it's not feasible to run an extension cord all the way up to space, so she's got 2 fixed solar panels that dump their power into some 120 watt-hour batteries. The solar panels provide enough power to fully charge your phone 9 times every 90-minute orbit if they're optimally pointed at the sun. But this actually creates a big problem for us. We have to point this way at the sun to charge up the solar panels, but then we have to point this way at the Earth to send and receive pictures, and then this way down into Earth to take the selfies. So how do we move around in space when there's no fuel or thrusters and there's no atmosphere to push against, so propellers won't work? Well, here's a hint. See this cube? It's just hanging by the swivel mount, and it doesn't have any thrusters or propellers attached to it either. And yet, when I push this button, I can get it to magically rotate and then stop. So can you guess what's going on inside to make that happen? Well, if we take off the panels to take a look, the trick is this spinning disc, or flywheel. Because angular momentum must be conserved, if the flywheel starts spinning one way, physics says the cube must rotate the other way to maintain equilibrium. So if you orient these 3 flywheels we call reaction wheels, all 90 degrees apart from each other, then you can spin them up and down to orient the whole satellite to any direction you want in space. And just like you can see here, they're incredibly precise. Now, because rotating the satellite is critically important for a backup and to help unspin these flywheels once they get to their max rotation speed, we've also got 3 torque rods, again all oriented 90 degrees to each other. These are super genius and are such a simple design, you can even make one yourself, where you just run a bunch of wire around a $2 piece of crystalline iron, and when you run a current through that wire, it creates a magnetic field. You can see proof of that here, because when we turn it on, it moves this compass. But that new magnetic field will want to line up with Earth's magnetic field, just like how normal normal magnets want to line up together. So you can see here, simply by turning it on and running current through the wire, seemingly by magic, you can change the orientation of this little floating platform. Another challenge we have is SatGus needs to know exactly where it is at all times relative to the Earth, so it knows when to snap your selfie as your neighborhood is passing underneath, along with a bunch of other reasons. To solve that, we've got a GPS on board, but that only tells us our location, not our orientation. So for orientation, we've got an IMU just like your phone does when it knows you've rotated it, as well as 2 star trackers that take pictures of the stars and match them against a catalog of star pictures to understand which way you're facing. But sometimes they can't see the stars because the sun's blinding them. So there's also 2 sun sensors that locate the brightest spot in the sky and just assume it's the sun, and those work great for course measurements. For the second to last critical piece of hardware, we need to be able to talk to it. For that, we've got 2 different radios, one slow and one fast. There's a UHF that has low data rates, and that's for basic commands and telemetry communication, and then an S-band, which is for higher data rates, like actually transmitting the pictures. And the final piece of hardware on SatGus that you're also going to need for your own space build is the flight computer. This is the brains of the satellite, and it takes all the inputs from the sensors and radios, and then makes the choices on where to spin and take the pictures. For step 2 of building and sending something to space, we need to analyze our design, because there are 4 main ways space tries to kill you. So we need to investigate each of these and make sure we're protected. The first is that it will try and shake you to death. Technically, this actually happens on the launch pad before you get to space, but the rockets necessary to escape the Earth's gravity are so massive and powerful, the violent rumble inside the rocket is strong enough to break most items we use on a daily basis here on Earth, especially if you're vibrating at the same rate as the rocket. And here's what I mean by that. You know how if you push someone on a swing at just the right time, they go higher and higher? Is that too high?
No.
Is that too high?
No.
What?
Higher.
Higher! But then if you push at the wrong time, you actually mess up their swinging and they slow down. Everything has a resonant frequency, from your phone right after it hits the ground to your house in an earthquake. To illustrate, I've got 3 masses here that all weigh the same. They're just attached to different rod lengths. So as I increase the shaking of this base plate, see if you can spot when we hit a resonant frequency. Oh, there it is for the long one. It becomes like the swing because we're adding more and more energy with each shake until it breaks. And now once again, if I increase how frequently this base shakes, or its frequency, and we go past the resonant frequency of the big one, now the longer rod is fine, but the middle one hits its resonant frequency, and now it breaks. Now if I do this once more, and maybe pause at the first resonant frequency, and maybe I pause at the second, and then I crank it all the way up, we get close, but we never quite hit the resonant frequency of the small one. And that's the key. The shaking base plate represents the rumbling, shaking rocket. We have to make sure all of our hardware has a resonant frequency above the rockets, just like the short one did, so it doesn't break off like the longer two. But how do we do that? Well, remember that CAD model we created in step 1 to organize and package everything? We put it to double use, because now we turn it into a finite element model. This means we take the whole structure and divide it into a lot of little chunks called a mesh. Each chunk is small and simple enough where we can use really basic physics equations to see how it will affect the chunks next to it if you start vibrating them. So now the computer just has to solve lots of really simple equations that are all connected, as opposed to one single impossibly difficult equation, to make sure that the resonant frequency for the whole satellite and each individual part are all higher than the rocket shake frequency. After that, even though we know we won't overlap with that low resonant frequency where things will go really bonkers, it's still a pretty violent shake. So we use that same finite element model to make sure all the pieces on the satellite are still strong enough to even withstand those lower level forces. The second way space tries to kill you is it wants to both burn and freeze you to death. Here on Earth, we've got a nice cozy atmosphere that acts like a giant blanket that holds in heat from the sun and moves heat around through wind, which keeps the temperatures relatively stable. But in space, there's no atmosphere and no wind. And so in a single orbit, parts of the satellite can get as hot as 212 degrees Fahrenheit in the sun, and then as cold as negative 112 degrees Fahrenheit in the shade. That's like going from nearly twice the hottest temperature temperature ever recorded in a desert on Earth to the coldest temperature ever recorded in Antarctica every 90 minutes. If we don't protect against it, those temperature swings would freeze or overheat the electronics pretty fast. So once again, we use that mesh that makes the math really simple. Only now we investigate how heat spreads through the metal structure when it's in direct sunlight or in Earth's cool shade. And once you've done that, you now know where to place the heaters, such as near the flight computers, so we can make sure it doesn't get too cold in the shade, and then surface coatings as radiators to make sure it doesn't get too hot in the sun. The third way space is trying to kill you is to sunburn you to death. An hour in direct sunlight in space is equal to an entire year of standing in the sunlight on Earth, thanks again to our protective, healthful atmosphere. So we need to effectively put sunscreen on the satellite by placing critical electronics behind a thick enough piece of metal or glass, or else the extreme harsh radiation from the sun and other sources would damage the electronics. But how thick should it be? Because we have a very tight weight budget and we can't afford to make an enclosure thicker and heavier than it absolutely needs to. Well, as an example of how we figured that out, we took our Google Pixel and placed it in a radiation chamber that mimics the harsh space environment, then blasted it with radiation, and it actually lasted about 10 minutes, which is pretty impressive. Plus, it looked really cool. And so now that we know exactly what amount of radiation causes phone screen failure, we can calculate how thick the aluminum and glass enclosure needs to be to make sure we stay well below that value. In our case, the necessary layer of sunscreen ended up being aluminum that's 6 millimeters thick and a radiation hardened glass that's 5 millimeters thick. Speaking of super advanced phones in space, we partnered with both Google Pixel and T-Mobile to make this whole thing happen. Google Pixel was the obvious choice to take the first ever selfie from space because of its specifically tested durability, bright high-resolution display, and the real tone technology that accurately displays all skin tones. And then T-Mobile because they're already partnering with Starlink to provide satellite coverage to keep you connected in places you never thought possible. So they were our experts when exploring how to communicate with our selfie satellite. And the fourth and final way space is trying to kill you is to vacuum you to death. We don't always realize it, but we're at the bottom of a huge dog pile of air molecules, which means our body is constantly pushing back against all that collective weight we call air pressure. But if you remove all that air pressure to mimic space conditions by sucking it out with this vacuum chamber, you can see exactly why astronauts need to wear an air pressurized suit when they're out in space that pushes in all around them as if they're on Earth. Now, of course, our satellite isn't carrying marshmallows, but it does have some rubber and foam and lithium batteries that once put in the vacuum of space can all puff out or release gases that could damage other equipment if we don't take all the necessary precautions. So there's a couple other small things to watch out for, like corrosion, but those are the four main ways space is trying to kill your future space creation. But you'll notice I didn't say you need to worry about crashing into other satellites orbiting in space. And this might come as a surprise if you've ever seen this picture that accurately represents the number of satellites and other objects currently orbiting our planet, because it looks really crowded. The problem is those satellites aren't drawn to scale, just as the airplanes in this representation of daily flights across the whole planet aren't drawn to scale. SatGus doesn't even need thrusters to avoid another satellite because the chances of a collision happening are so incredibly low. In fact, if you calculate based off volume of usable space occupied in orbit in a given day, space is 1 million times less crowded with satellites than our skies are with airplanes. And then think about how rare it is to ever see even two airplanes close to each other in the sky. So space is 1 million times less crowded than that. As humans, we actively track all 44,000 satellites and objects orbiting the Earth larger than a baseball. And there's international rules now. If you put a satellite up into orbit, it needs to burn up and disintegrate after a few years. So before we move on to step 3 of our mini space program and actually build the dang thing, now's a good time to point out SatGus will only be alive and orbiting anywhere from 1 to 3 years before it burns up upon re-entry. So if you want that space selfie, you're gonna wanna get yours now by visiting spaceselfie.com or using the link in the video description. Once you're on the site, it's pretty straightforward. You just upload the selfie you want and then choose things like if you want the daytime or nighttime Earth photobombing you. You can also select if you wanna take the picture over your hometown, and then we'll tell you exactly when we're gonna snap the picture. So don't forget to go outside and wave at that very moment. And when you submit your picture at spaceselfie.com, not only will you get this free, super cool mission patch in the mail, but it means you also have a chance to come out and watch the rocket launch in California in a month or two with me and my team. Now, of course, all this is free if you're a current CrunchLab subscriber, or if you become one now if you want that perfect holiday gift.
Yes!
Otherwise, all you gotta do is sponsor one box for a kid who can't afford it. Either one's a great choice. But I'll just point out, if you're like me and one of your favorite things in life is experiencing those aha moments where you learn something new, like maybe that's even happened watching this video, and if so, you're gonna love the Crunch Labs Build Box if you're a kid, or the Crunch Labs Hack Pack if you're a teen or adult. In both cases, they get delivered right to your door, where we build them together and learn all the really cool science and physics that make them work. For example, Build Box subscribers already learned all about the flywheels we talked about earlier in the video, because the first mechanical toy we put together is this super fun mini disc launcher, where the physics principle we discuss in the exclusive video for me is flywheels. And for Hack Pack, we take it up a notch with a really cool robot that will work right out of the box with no programming required, but then as a fun incentive to dig in and tweak the code, we make it easy to level up the robot's capabilities using the online coding module. And since the holidays are here, there's nothing more fun to put on your list, nor is there a better gift to give than an investment in the future of that favorite person in your life as you watch their confidence, understanding, and resilience grow. On top of that, I promise you'll be guaranteed to be the first person that has ever gifted them a picture of themselves actually in freaking outer space. So to get all that, just go to crunchlabs.com or use the link in the video description, or to say thank you, we're giving away either 1 or 2 free boxes as a holiday special. Alright, so now that we've completed step 1, the design of our satellite, and then step 2, by doing all the math and analysis to make sure it will survive the brutality of space, we finally have the confidence to start step 3, actually building it. And as is tradition here, we're just gonna knock it out in a 15-second build montage. Once your space hardware is all put together, you're going to want to run through a full hardware-software test to make sure everything is working exactly how it was designed to. So for us, that includes things like unfurling and then testing the solar panels, test deploying both our camera and our screen, and running a full selfie upload and transmission test. Now I mentioned earlier, SatGus actually has 2 screens and 2 space-hardened Redwire cameras. Now hopefully we never end up using the redundant backup set, but it's there just in case the first one stops working for any reason, because we can't exactly just go up to space and fix it. This is actually pretty common when designing things for space, especially for mission critical items. Even my own hardware I designed for the rover had a backup. Both these doors could open and accept an individual dirt sample from the rover arm, even though the dirt actually went to the same place to get analyzed. So once everything looks good, all you need to do now is sign the thing and then add some googly eyes. Okay, fine. Sadly, googly eyes aren't allowed in space. Now that it's officially built and everything seems to be working, it's time for step 4, which we refer to at NASA as the shake and bake. Basically, when we analyzed the design in step 2, we predicted how SatGus would respond to the extreme vibrations and temperature fluctuations from launch in space. Now it's time to run some tests by shaking it and baking it to reassure ourselves that our predictions were accurate. For the shake part, we attach SatGus to a shake table and shake it in all 3 directions for 1 minute. We also shake it at a bunch of different frequencies to make sure there aren't any unexpected resonant frequency issues with any of the hardware. Now the intensity of the shake is a little bit more than what it will see on the launch pad, so if she survives this, we now have both analytical and actual proof she'll survive the ride to space. We're also checking to make sure nothing comes loose. For example, if you don't glue your fastening hardware down, as you can see here, all the vibrations can actually cause them to unscrew themselves. For the bake part, we put SatGus in a vacuum oven, just like space, and then cycled it to the maximum and minimum temperature 3 times, and even operated the satellite at these temperatures for extra peace of mind that once again, both analytically and practically with the test, when she gets to space, she'll have no problems with the vacuum and she won't freeze or burn to death. So once you're done with the shake and bake and you do some final tests to confirm everything's still working perfectly, now you can load it into its launch dispenser and pack it up. When you get to orbit, the dispenser will stay attached to the rocket, but the ejection spring mechanism inside it will gently push SatGus out to space. Another nice feature of the dispenser is that it has rubber isolation dampers where it attaches to the satellite. This serves to further limit the amount of shaking the satellite will feel. It's the same kind of thing tall skyscrapers use to limit how much shaking they feel from an earthquake. You can see how much this tower shakes when directly attached to the shaker table, but if we separate it with rubber pads, now you can see the shaking is greatly reduced. So now with everything packed up and ready to go, the next stop is step 5, the launch pad. SatGus will be launching on a SpaceX Falcon 9 from Vandenberg Space Force Base in California. Now when you launch your own creation to space, space, I recommend SpaceX because they're currently the most inexpensive option by far. Also, when you book a spot on the rocket, the website makes it feel like you're just ordering a pizza as you select all the options you want, such as which orbit, launch date, interface plate options, or even add-ons like extra fuel. Now, Vandenberg might seem like an odd choice to launch from, but it's really strategic. Because we want to take satellite pictures over every spot on the Earth, we don't want an orbit that circles this way around the Earth. We need an orbit that circles this way, so we have full coverage of every spot as the Earth rotates underneath us. Fun fact, spy satellites also have orbits like this, so they can also take pictures anywhere on Earth. So to get this kind of orbit, we need to launch to the south, and for safety reasons, it needs to be over water. And this makes Vandenberg an ideal choice in the United States. Now, if you're sending something to Mars and you need to escape Earth's gravity, for that you want to be as close to the equator as possible because you save fuel by taking advantage of the fact that you're already moving 1,000 miles per hour to the east as the Earth rotates versus 0 miles per hour to the east if you launch from, say, the South or North Pole. This is why in the United States, those missions either launch from here or here because they're as south as possible and both launch east safely over water. Now, SatGus won't be alone on this trip. There'll be anywhere from 50 to 100 others hitching a ride, all contained up in the nose part of the Falcon 9. That portion that carries the thing you care about putting in space is called the fairing, and on the Falcon 9, it's big enough to house a school bus. Then down below at the bottom, you've got a big liquid oxygen and fuel tank that power 9 engines, and then a smaller identical set near the top with a single engine, because these two parts will eventually separate when we get to space. So after a very dramatic and very powerful liftoff sequence, with the equivalent energy of setting off nearly 8,000 sticks of dynamite, the Falcon 9 launches off the coast. It takes about 2.5 minutes before it's traveling at 3,700 miles per hour. Now it's time for the main booster to separate from the top portion where SatGus is stowed away. What's really cool though is that it falls back to Earth and then eventually flies itself autonomously back to a landing pad so it can be used for another flight. This is one way SpaceX is able to fly things so much cheaper, because boosters used to not be reusable and you'd have to build a new one for every single flight. Now the remaining single engine fires itself up for the first time to keep building up some speed, and 30 seconds later, 3 minutes after launch, the fairing splits in two and peels off, exposing all the satellites as the engines continue to fire. It then continues accelerating for an additional 5 minutes, getting up to a speed of 5 miles per second, which is about 10 times faster than a bullet, at which point, just 9 minutes after launch, it cuts off the engines. Now it will just silently coast for close to an hour, after which it will take about 2 hours to deploy each of the satellites, including ours, one by one, as it completes an orbit around Earth. And this brings us to our 6th and final step of our bootstrapped space program, which is operations. Once SatGus ventures off on her own, after a couple hours, we should hear back from her saying everything's going great. After that, she'll stretch out her solar panels and then deploy the screening camera. We'll be monitoring all her vitals from this mission control room here, and after a couple weeks, when everything is confirmed to be in perfect working order, she'll start taking the selfies. And she'll keep taking selfies every single day until she reaches her honorable end in approximately 1 to 3 years. And this might seem sad, but there's no way around it, because as her orbit decays over time, she starts bonking into more and more air molecules as the atmosphere gets thicker and thicker, slowing her down even more. And because she has the energy of a 55-pound cannonball traveling 10 times faster than a bullet, heat builds up dramatically from so much air friction, and she disintegrates spectacularly in a glorious hot fireball. And to give you a sense of just how much energy this actually is, this is a model of our satellite subjected to only 5 sticks of dynamite, or 1/100th the re-entry energy. Which honestly is a pretty epic way to mic drop a mission fully accomplished. I've been working on creating this satellite with my team for over 3 years, and after all that, we're currently right here in our 6-step space program, with launch happening in a month or 2. So let's do this together. Go visit spaceselfie.com, upload your picture, then I'll send you the free mission patch, and maybe you'll even be selected to come out and watch the launch with me. Since I was a kid, gazing up at the night sky has filled me with such wonder. And seeing all the stars, and even our own galaxy, and thinking about our place and potential as humans amongst all those stars, sparked my first love for science, and eventually led me to Mars. So in some small way, sharing that wonder with all of you feels really special, and fills me with hope for the next generation of big problem solvers.
Let's do this.
With the holidays right here, what about getting or giving a different way to think? Or how about even a free college tuition?
That's awesome.
Well, in either case, Crunch Labs has you covered, because every hack pack has a chance to contain the Platinum Diploma. If yours has it, college tuition is free for you or someone you love. And as for the thinking part, of course, you get that for kids with the build box, but for teens and adults, if you've always wanted to make and build cool stuff, but just haven't figured out that first step, Hack Pack is it, because you're getting a series of really fun programmable robots that get delivered right to your door, where we build it together and learn step by step the kinds of engineering skills that go into making the builds on my YouTube channel. And they work with no programming required, but since my goal is to take you from wherever you're currently at and then level you up, you can easily hack the microcontroller brains of any of these robots in a bunch of ways to completely level up the functionality. There's also a community where you can share your builds and post your questions, as well as an AI chatbot named Mark Robot that will check your code and even help you implement your most creative ideas. So no matter what your age, this holiday season, if you want to grow your brain in really fun ways and get or give someone their actual picture from actual space, just go to crunchlabs.com, use the link in the video description where to say thank you. We're giving away either 1 or 2 free boxes as a holiday special. Thanks for watching. You know you're a true Crunch Labs fan when you watch my videos all the way to the end. And for those of you who made it this far, I've got something incredibly special as a reward. Starting November 16th, while the discounts last, you can now get 20% off your Hack Pack subscription. And I know what you're thinking. Does this apply to BuildBox too? And the answer is yes. So whether kid, teenager, or adult, you're getting 20% off growing your brain in delightful ways. YouTube is offering this amazing discount to show off the very cool shopping features they've built into the platform. So you won't find this deal anywhere else. To claim your discount, just click the YouTube shopping button on the video and add a subscription to your cart, and the discount will magically appear at checkout. And you'll get the biggest bang for your buck, of course, if you choose to pay annually. But hurry, because this offer is only good while the discount's still available, and there's more info for you in the video description. So thanks to YouTube shopping for this fantastic opportunity you're not gonna want to miss.